In this video, we'll be exploring activation functions, which are a key concept in deep learning. We'll start by examining the characteristics and limitations of the sigmoid function, one of the most common activation functions. In future videos, we'll look at other functions developed to address some of the sigmoid function's drawbacks. To make activation functions easier to understand, let's use an example based on grading methods. One way to evaluate grades is a binary system, where students either pass or fail based on a threshold. For instance, in this method, anyone scoring 50 or above would pass, while anyone scoring below 50 would fail. However, if a professor were to grade solely using a binary system with only A and F grades, it could lead to unfair results. For example, a student who scores 51 would receive an A, while a student who scores just 2 points less would receive an F, which doesn't seem reasonable. Also, a student with a score of 90 might feel it's unfair to receive the same grade as someone who scored only 51. Therefore, in some cases, it may be more appropriate to use a grading system with multiple categories like A, B, C, D, and F to provide a fairer evaluation. In one of the previous videos, we talked about the perceptron, which is a foundational building block of deep learning. Inspired by human nerve cells, or neurons, the perceptron is a basic component of artificial intelligence. Its structure consists of input values, a linear combination of those inputs, an activation function, and an output value. In the early perceptron model, the activation function used was the step function, which outputs 1 if the x value is greater than 0, and 0 if it's less than or equal to 0. So, like the previously explained pass-fail grading method, the step function operates as a binary classification system. Let's explore the limitations of the step function through the training process of an artificial intelligence model. In the first training iteration, the weighted sum and bias are calculated to be negative 0.3. Since this value is less than 0, the step function outputs 0. In the second training iteration, the weights are updated and the weighted sum and bias are reduced to negative 0.15 from negative 0.3. However, since this value is still less than 0, the step function again outputs 0. This means that even as the model learns and updates the weights, small changes do not affect the output, which remains fixed at 0. Building on the previous explanations, let's examine the limitations of the step function. First, the step function is a binary output function, meaning it only outputs 0 or 1 based on a threshold. This can make precise model training challenging. Next, the step function is not differentiable. Being differentiable means that there should be a defined tangent at every point, but the step function has a sharp vertex where it transitions between 0 and 1, making it non-differentiable. As a result, while it can be applied to non-linear problems, it cannot use gradient-based optimization algorithms commonly employed in neural network training due to its lack of differentiability. Finally, the step function is not effective for performing complex learning tasks. Because of these limitations, neural networks tend to prefer activation functions that are continuous and differentiable, such as the sigmoid function. Now let's look at the sigmoid function, an activation function often used in neural networks to overcome the limitations of the step function. Also known as the logistic function, the sigmoid function is defined as 1 divided by 1 plus the natural constant, e, raised to the power of negative x. As a result, it outputs values between 0 and 1 for any input x. When x is small, the output is close to 0, and as x grows, the output approaches 1. Additionally, while the step function outputs the same value for all x values that are greater or less than 0, the sigmoid function provides a range of values between 0 and 1 based on the input x value. This allows it to represent subtle differences that the step function cannot distinguish. Furthermore, since the sigmoid function forms a smooth, continuous curve, it is differentiable, which enables the use of gradient-based optimization algorithms, such as gradient descent. This is a highly beneficial feature in neural network training. Let's look at another characteristic of the sigmoid function. In an artificial neural network used to solve classification problems, if we assume the sigmoid function is used as the activation function, it outputs values between 0 and 1. This allows us to interpret the output as a probability rather than a simple number. For instance, in a classification task where we need to choose between two classes, say cat and dog, using the sigmoid function, an output value of 0.8 for cat and 0.2 for dog would mean there's an 80% probability that it's a cat and a 20% probability that it's a dog. This makes the sigmoid function especially useful for binary classification problems. Even such a useful function as the sigmoid has some limitations. First, as x becomes larger or smaller, the gradient at the ends of the function approaches 0. As a result, even if the differences in input values become very large, the difference in output values hardly changes, meaning the problem seen with the step function, where input differences are not reflected in the output, can reappear at the extremes of the sigmoid function. Additionally, in neural networks, when the output values of lower nodes are input to upper nodes, the sigmoid function's output is always positive, which tends to cause the input to the upper nodes to grow larger. In other words, as the input increases, the corresponding gradient approaches 0, reducing the gradients required for backpropagation, which will be explained later, and leading to a problem known as the vanishing gradient. This can prevent the neural network from adequately learning. Let's explain another limitation of the sigmoid function. For example, let's say we have two input values of 1 and 2, and after multiplying these by their weights and summing them, the result is 0.7. Passing this value through the sigmoid function gives an output of 0.67. Now, if the actual value is 0.3, the error between the output and the actual value is 0.37. To reduce this error, gradient descent will adjust the weights in a direction that decreases their values. If we assume weights O1 and O2 decrease to 0.25 and 0.15 respectively, then recalculating in the same way gives an output of 0.63, showing a reduction in error compared to the initial output. In this way, when the sigmoid function output is greater than the actual value, gradient descent updates the weights in a direction that aims to decrease all of them to reduce the error. Now let's consider the situation where the output of the sigmoid function is less than the actual value. Using the same example as before, let's say we have two input values of 1 and 2, and after applying their weights and summing them, the result is 0.7. When this is passed through the sigmoid function, the output remains 0.67. If the actual value is 0.9, the error between the output and the actual value becomes negative 0.23. To reduce this error, gradient descent will adjust all the weights in a direction that increases their values. If we assume that weights omega 1 and omega 2 increase to 0.35 and 0.25 respectively, then recalculating in the same way yields an output of 0.7. showing that the error has decreased compared to the initial output. Thus, when the sigmoid function output is less than the actual value, gradient descent will update all weights in a direction that increases them in order to reduce the error. This means that both weights omega 1 and omega 2 are updated in the same direction. To summarize, we can see that in the sigmoid function, the weights are updated in the same direction. This is because the sigmoid function has a non-zero centered property, meaning it does not center around 0 and always outputs a positive value between 0 and 1. As a result, there's a higher likelihood that weights omega 1 and omega 2 will be updated in the same direction. This often leads to both weights increasing or decreasing simultaneously, which means they continue to be updated in the same direction, as illustrated in the green area of the diagram. For example, the first point might move in the second direction, where both weights are increasing, and then move in the third direction, where both weights are decreasing, creating a zigzag pattern that repeats. This results in an inefficient learning path, which can slow down the learning speed. Therefore, due to these limitations of the sigmoid function, various other activation functions have been developed. In the next video, we will explore activation functions other than the sigmoid function.